Pour water into a glass, and physics behaves exactly as expected. Gravity pulls the fluid down, forcing it into a level, horizontal surface. Place a wide glass tube into that water, and the liquid inside matches the level outside. Gravity treats the water inside and outside the glass the same way. But look what happens when we swap that wide tube for a remarkably thin one. A tube so narrow, physicists call it a capillary, from the Latin word for hair. The moment the glass touches the surface, the water inside the tube climbs upward. It climbs past the surrounding waterline and rests significantly higher. Gravity is constantly pulling downward on every drop of that fluid. We need to identify the upward mechanism powerful enough to lift this water against that pull. To find the answer, we have to look at the exact microscopic point where the top of the water meets the inner wall of the glass tube. Water molecules are highly attracted to the molecules in the glass. This property is called adhesion, and it makes the water want to spread out and wet the solid surface. Because of adhesion, the water's edges physically grip the glass and pull up, creating a sharp contact angle, or theta. Meanwhile, the rest of the surface is held by surface tension, acting like a taut, invisible skin connecting the liquid's edges. As the edges pull up on the glass and the surface tension pulls the center tight, the top of the water column deforms into a U-shaped curve. We call this a meniscus. This curved shape creates a specific physical result. Pressure always drops on the convex side of a curved liquid surface. Standard atmospheric pressure pushes down from above, but right below the meniscus, pressure drops. Drawing a horizontal line across the main level shows the outside water feels the full weight of the atmosphere. Inside the tube, at that exact depth, a low pressure deficit remains. Fluids move to balance pressure inequalities. The high atmospheric pressure outside forces the water in the beaker to quickly rush into the lower pressure zone inside the glass tube. The high-pressure reservoir at the base of the beaker physically drives the water upward to fill the pressure deficit created at the top. With a constant upward push from the bottom, we have to ask why the water doesn't just shoot out the top of the tube. The rise stops because as the water climbs, it gathers mass, building a heavy liquid column. This growing column exerts its own downward pressure. The force of that pressure is determined by the fluid's density, the pull of gravity, and the height of the column. The upward motion stops at the exact moment the weight of this new water column perfectly matches the pressure deficit created by the meniscus. A stationary column of water in a capillary tube is a physical record of two massive forces locked in a state of perfect equilibrium. This is the capillary rise equation for the exact point of equilibrium. Focus on A in the denominator, representing the capillary tube's internal radius. Because A is in the denominator, we have an inverse mathematical relationship. If you make the tube narrower, decreasing A, the height of the water must increase. You can see this math play out in the physical world. As a glass tube shrinks in width, the water is driven higher and higher to maintain the pressure balance. Capillary rise is the predictable, measurable result of surface tension, contact angle, and pressure differences working together to temporarily defeat gravity.